I'm just making a video about how to do Thenevins equivalent and Nortons equivalent. I see that whenever I look at Thenevins equivalent videos or Nortons equivalent videos on YouTube, there's not many videos on how to do it the normal way. There's a lot of videos doing it using nodal analysis and mesh analysis, but sometimes not a lot of circuits apply to that or can be able to use that method, so I'm going to show you how to do it properly. Now, you need to understand how to do Thenevins and Nortons. So when you find Thenevins or Nortons resistance, you need to open the RLs and disable all the sources. You need to open RL to find Thenevins voltage, and you need to find Nortons current by shorting RL. Now, it can get tricky when you're trying to find Thenevins voltage with a current source, and the way you do it is that you use the current rules and then solve it with Ohm's law after that. So if there was a current source and you were trying to find Thenevins voltage and the circuit was parallel, then you would use current divider rule, which is the one over here, and use Ohm's rule after that. Now, the other way is called Norton's current, and with a voltage source, you need to use voltage divider rule, which is this one, on a series circuit, and then use Ohm's rule. This is quite a complex Thenevins circuit, but the more you break it down, it will become much more easier. As you see, we've got a current source there, and we've got 3 voltage sources. So it's quite a lot to work through. So the rule is, when using Thenevins or Nortons, is that you do superposition, and what I mean is when you're disabling sources, currents open circuits and voltage sources always short. Now, to get the Thenevins resistance, you disable everything and open the load. The way you look at it is that this circuit here is opened, so you don't need to worry about that. Now, the way you look through it is you go through either the A or the B node, and you figure out how, if it's currents in parallel or in series, and then you add them all up. So the way that I always do it is I'm imagining a current that's just going through there, and then it splits in between. So I know that these resistors are in parallel, so it will be 20 times 20 over 20 plus 20, because that's how you do your parallel formula, which will be 10 ohms. Now, we figured out the Thenevins resistance, and now we're going to move on to the Thenevins voltage for each sources. Now, this is one of the sources with all the other ones disabled, the 20 volts on the top. Now, the way to solve it, right, is to look at where the resistors are. So you're meant to be measuring the A and the B node, but there's nothing there. So you put your A, B nodes there, that's your new ones, and you solve for this resistor. This 20 ohm resistor, it doesn't matter anymore. It doesn't contribute to anything because of that open circuit. So you ignore that. When you try to figure out the Thenevins voltage for this, you imagine a voltage going through, and you realise that it goes to the B node, and it goes all the way to the A node. So that means if it goes to the B node before the A node, that means it's going to be negative. So it'll be negative 20 for this. And if you realise that these two resistors are in series as well, because none of it splits, it's a full loop. So you do the voltage divider rule. You do minus 20 times 20 ohms. You get 20 from here. And then you do 20 plus 20, which is the other 20 from here, added together to this. This gives you an equivalent of minus 10 volts. So that's your contribution for the 20 volt source from that one. You follow the same rules as the one that I just done for the 20 volt source. This doesn't contribute to anything. You do the A and the B node there. So you see it's a series loop again, as you see from the voltage loop. This becomes 40. It's going to be positive because it reaches A before B, and it'll be times the 20 over 40. It's going to be this 20 over there, those are over here. This should equal about 20 volts, I think. Yeah. Now, this is the harder one, where you have a current source instead of a voltage source, so it can become a bit more confusing. So, I want you to treat it as like you're solving for a Norton's current. So, the way you would treat it is if you have a current source, if the resistors are in parallel, then you do current divider rule, and then if the resistors were in series, you would do Ohm's law. So, this would be your A and B node, your new ones. Now, to picture this, the current's going through here, and now it splits between. So there's going to be different values for each bit. So you do current divider rule. Now, the 8 amps is going to go through A before it goes to B. So it's going to be 8 over here, and then you'd multiply it. So the weird thing about current divider rule, right, the resistor that you want, right, it doesn't go to the top. It's the opposite one that always goes to the top. So you do 20, this is your 20, and then you do 40, this is 20 plus 20 under there. So it's 8 times 20 over 40. If you look in your calculator or type this in, you will get about 4 amps. Now, you've got a current now. So, the way to set this up is that you do 4 amps times the resistor that you want to get the value of. So, it would be 4 amps times 20 ohms. That's where you would get 80 volts. So, there you go. You have now finished all 4 sources of your... You've done all 4 voltages, and now all you need to do is just add them up. Now this is a bit harder to picture, right, because the A node is right next to the voltage source. So the way that I would do it, right, I would flip it so that this voltage source is still here, 20 ohms, then 20, actually no, I'm going to draw it like this. Remember, this is gone, so I'm just picturing it like this. That's gone, by the way, just to make sure everyone knows. And the 20 ohms here, the A and the B nodes here, and we can find our Thenevins here. So basically, I took this 20 and I put it here, and that I just moved over there. So that's how I would do it, and I just do 40 times 20 over 40. That would equal, what was it, 20 volts. Now, you figured out your V1, your V2, your V3, and your V4. All you need to do is just add them all up. So it was 20 plus 20 plus 80 minus 10. That equals to 110 volts. And there you go. That's your VTH. Now, you can take this a step further and draw the VTH circuit, which is, that's the Thenevins resistance, which was 10 ohms. And this was the load, which was 100 ohms. Now, just draw 110 volt, right, 110 volts there. This is the Thenevins equivalent circuit, right? If you wanted to do a Norton's, it's not in series, but it's in parallel, because that's how you treat it. So the way you draw it is like this. That would be your Norton's current, and that would be your load, no, not Norton's resistor, and that would be your load resistor. You can take this a bit further by doing trying to find the load voltage, which is, you need to know the load current equation, which is 110. Oh, sorry. It's the Thenevins voltage over the Thenevins resistance plus the load resistor. You do that by just putting it all in. 110 over 110, because it's both of them. That equals to 1 amp. Then you do the equation for the load voltage would equal to IL times the load resistor, which would be 100 volts. That's how you do it. It's easy. So we're going to try another example where with an inductor and a capacitor. I've took the time to split it all already, so it'd be quicker. So I'm going to do the Thenevins resistance first. You imagine the current's going through here, but then realise that there's an open branch here, so you get rid of that. And then it will go from 10 to 5J. And so it would be 10 plus 5J. That's your Thenevins resistance. Then on the voltage source, you look at, there's the 10 volt source and the current source is opened. You go through here and you realise that there's an open branch like last time, so you'd get rid of that. But you realise there's a gap between the A and the B as well, so the voltage doesn't change. It would stay the same because there's nothing inflecting onto it. Now the next source is a current source, which is a bit different. So like I said in it last time, just stick with the current rules. You don't need this because there's a gap in between, so it's just a full loop. Currents are going through here, use your current rules. Currents in series are always the same. That's 2 amps going through here, but using Ohm's law, you need to figure out where the A and B node is. So I would use this as my resistor because the way that I would draw it is, well, my inductor, sorry, is that I would make it as AB is here, and then minus J10 is there. That's how I would imagine it. So the 5J is my resistor I'm going to use for Ohm's law, 2 times J5, which will equal to 10J. So my contribution is 10J plus whatever I got from there, plus 10, and that is my Thenevins resistance. Now, I'm going to refresh you on about trying to figure out Thenevins resistance, because sometimes you think you've got it, but sometimes you realise, hang on, maybe not. So, for this, I'm going to imagine that the circuit gets changed every time. So, the load resistance is going to be 10 ohms for the first one, then J5, and then minus J5. So, we're going to do it through the 10 ohm resistor now. So, imagine that's our node, A and B. Remove that. In the previous few examples, right, when there's an open branch, I always say to get rid of it. Not in this case, because the current is actually going through here now this time. And then it's splitting in parallel with all those other resistors. Or impedances, if you want to be fucking bent about it. Now, the way to do this is, right, just add all your like terms for ones that are in series, and then put it all together. So the way that I would do it is, I would put these in parallel, and then add these two after. So you would do 5 plus J5 times minus J5. The way that I would do it is, my calculator has complex ways. The manual way, you'd have to set this to polar, and then set this to polar to times and divide, but this way is just easier in my head, and I'm just showing you how to do it. So 5 plus J5, what the fuck? 5 plus J5 plus minus J5. You put that in the calculator, you would get about 5 root 2 minus 45. You can simplify that to decimals to 7.07 minus 45, and then you'd add this bit, which would be plus the 2 minus 2j, and that would equal 9.89 minus 45. Remember, check your working, put it in the calculator. Don't make any mistakes, because it will fuck you up later on. Now, let's try it for the other one. So, put back our 10 ohms, and it's J5 this time. So, open that, make that our A and B node, just like that, and there you go. So, this bit can just be all collected. It would be 12 minus J2, and you would have minus J5 hanging in there as well. So the way I would do it is these two are in parallel, because when you look through it, the current splits between them and it goes back to normal. So just do it as 12 minus J2 times minus 5j over 12 minus J2 plus minus 5j. Sorry, I've mixed all the j's, I'm sorry, but it still works. And then that would be 4.38 minus 69.2 if you put it in the calculator, and then you'd add your 5 because that's in series with those resistors. Okay, that's with the 10 ohm resistor, I think. Oh, sorry, J5. So just write that there again. Now the next one is minus J5, and that's where you would open this bit. You get rid of your A and B's and put them over here. Now the way that I would do this is that these are just all in parallel with each other, because if you go from the B node this time, that's all in series together and that's all in series together, but they split. So it would be 12 minus J2 times 5 plus J5 over 12 minus J2 plus 5 plus J5. There you go. Put that in the calculator. That will be about 4.98, 25.53 degrees. However you round it. Now, we've got another AC Thenevins circuit. I'm going to do the same thing I'm going to do last time. I'm going to solve the Thenevins resistance first. Short that. That'll be minus J5. 10 ohms is over there. J10 ohms. A's over there and B's over there. Cool. So you need to look through all the terms. Go in here. J10 is over here. Then it splits. So 10 ohms and minus J5 are in parallel. So do times 10 times minus J5, 10 plus minus J5. That will, if you put that in the calculator, that will be 2 minus 4J. Add the 10J ohms. That's it. So it will be 2 plus 6J. You found your Thenevins resistance. There you go. Now, you do your sources. So we'll do 10, 0 over here, plus 10 ohms here, minus 5J ohms. Fucking hell, that's shit writing. pardon that. A and B, and 10J ohms is over here. Now, alright, that's fucking messy, right? But just bear with me. So, that doesn't exist anymore. Remember that. A, B, like we done before. It's just repetition. Then you see it's a series circuit. It goes there, goes right back to there. It's in a loop. So then you do, remember, positive is going to A first. Then that you do, what is it? 10 times minus 5J because of that, over 10 minus 5J. That equals to 2 minus 4J on the calculator. Once you do that, you add, what is it, your other contribution. 10 ohms is over here, minus 5J ohms is here, 10J ohms is here, plus the 3-volt source. What the fuck does this? Alright, this looks shit, but it works, okay? So, the A and the B are here, right? But you also realise that you've got a parallel circuit. That means your voltage is going to stay the same, because it doesn't matter that your A and B are far away from that. It's still parallel, so it'll be the exact same, but it goes to B before it goes to A, the positive, as you can see from here. Well, it's the same thing, right? So it will be minus 3 volts for that second contribution. That's your first contribution. So then it will be about, if you add them together, you should get something like square root 17 minus 104. Then it should be about 4.123 minus 104 degrees volt. Something like that. But you get the general idea. Okay, with this one, it's a bit more complex. It's a Nortons current we're looking for. Sorry for all the Thenevins examples, but they seem a bit harder than all the Nortons ones I can find. You've got a circuit like this. 20 ohms. Well, actually, no, let's solve for the Norton's current now. It's the same thing as the Thenevins, but I'm just going to call it Nortons because we're doing a Nortons. Go for here. A, B, 20 ohms, 30 ohms, minus J30. Okay, so there's a lot of component values. It looks quite intimidating, right? But it won't be that bad once you get through it. Now, see, the current imagine a current that goes through here, right? And it splits, so you know that these two are in parallel. But what you also you see as well is when that goes through, they split too. So I want you to try simplify the circuit. The way that I would interpret this is that I would put these in parallel first, so it would turn into this, and then put my A and a B node there, and then 30 minus 30J. Right? That's how I would do it. So, do this first. You would get 8 plus 4J. And then you'd add that, because that's in series with that. Plus the 20, you would get 28 plus 4J. And then you just remember, these are in parallel as well. So you just need to do a parallel circuit and another parallel circuit. So a parallel circuit with another resistor, then make that parallel with the other resistor. Well, the other set of resistors. So it would be 28 plus 4J times 30 minus 30J over 28 plus 4J plus 30 minus 30J. If you do the maths on a calculator, it will be Norton's resistance for that, will impedance, whatever you want to fucking call it, I don't care, is 18.88 minus 12.72 degrees ohms. That's how you do that. Now, let's calculate how to do each source now. The way I would do it is, this time it's a voltage source, so remember the rules. You just need to do the voltage rules, but then use Ohm's law after this. Make the circuit 20 ohms. Alright, remember, when you're doing a Norton's current, you short the A and B now. So it's like this. You can represent it like this. J20 and 10 ohms. See, now, the rest of that circuit, that doesn't exist anymore for this. You're just finding the A and the B node. It doesn't matter. You can move that 20 over here if it makes you understand it better. Like this. One sec. There you go. They're in parallel, and the voltage will just be the same when you do that. So it would be 30 and 90 over, you need to find the total of the resistors, so it would be 20 times J20 over 20 plus J20 plus the 10. The mass will come out at like 20 plus 10J, I think. If you don't understand how I got that, those are in parallel, add that. And then, getting ahead of myself, the current will be 20 plus 10J, and that should equal to 1.34 63.44. Now also, that was just the total current in that. You need to figure out you need to do current divider rule again, because they are in parallel, right? They're in parallel. So that is just the total current. You've not figured it out properly. If I get rid of this, you're figuring out this resistor, right? So you do current divider rule again. Well, not again, but for this, you do, why the fuck am I doing red? You do 1.34 63.44 times, remember, with current divider rule, you need to do it from, you need to use the other resistor, so it'd be J20 plus J20 over 20 plus J20. There you go. And then put that in the calculator, you would get 0.95, 108.44 degrees amps. That's your first resistor, right? So, no, sorry, your first current, right? So this one's got an extra step to it. It can look confusing by doing it, but once you get a bit of practice, you'll understand it. Because the next one is another voltage source, and it's going to be 20 degrees volts minus J, what was that? Minus J 30. Then it's 30 ohms. A, B. That's all that really matters, to be honest. Remember, it gets shorted. You see, it's all in series. So, I'm sick. Alright, so for the, it goes to the B node, right? Sorry, my bad. For the, this loop doesn't exist. It's the other way. This is the right way. I didn't realise there was a plus. So it goes to the B node first. So it's minus 20. But you also realise you could also just figure out by Ohm's law, because the minus 20 over there and the 30 over 30 minus 30 J30, right? That will still equal to the same current. The current in the series will be the same, if you get what I mean. Because when resistors are in series, the current stays the same. So all you really need to do is just figure out the total current for that, and that'll still be the same. So you could just do you do this formula, and then you will get 0.47 minus 135. That's your contribution for the second one. So if you didn't understand that, right, the reason why I didn't use voltage divider rule, then used Ohm's law, is because this whole bit here is just a series current, and current just, what is it? If I just figured out the current for this, it would still equal the exact same. So I got 0.47 for that, with minus 135. And then I got 1.34 is 63.44 degrees as my other contribution. You add them together, and then you'll get 0.85 138 degrees amps. If you really want to draw the circuit for it, you can. It'll be 0.85 138 degrees amps. Then Zn would be 18.88 minus 12.72, and your load, wait, no, sorry, my bad, I've drawn this as a Thenevins circuit. It'll be 18.88 minus 12.72 here, and then the load, just not a load here, but you get what I mean. If there's a load here,